All right. This is a short recording here that I want to do to introduce you to logistic regression part one. And I want to do this by going back and giving you a little bit of history of chi-square tests and demonstrate how those fit in with what you're going to be doing in logistic regression. So bear with me and we'll talk through this. So my presentation starts here with a little bit of introduction and history. And there's really three people out there that are kind of interesting regarding the history of chi-square tests. And probably the most important one is this guy named Carl Pearson. And it was around 1900 that he did the original work for the chi-square test and also for that distribution. But there was another guy out there sometime before him back in the 1860s, and it was a guy named Mendel. And he was a monk that he started out, he really wanted to be a teacher, and he tried a couple of times to get approved as a teacher. And he couldn't make it. And so he was off working as a monk, and he was doing these experiments with peas and making predictions about the ratios of the experiments that he was performing there. And his work actually led to the field of genetics. And so this guy became very well known, and then he kind of gets tied in with Carl Pearson and some other people. And then later on, early on in the 20th century, R.A. Fisher, he was a well-known statistician, and he gets into this picture too. And then if you fast forward to the 21st century, we're finding all sorts of uses for the chi-square distribution, way far from its original roots there. And part of the reason for this is the chi-square tests were introduced as goodness of fit tests. Well, that has a lot of applications for us. But let me just give you a brief picture here. If you picture data that you've collected, and you think it follows some sort of a pattern. For example, it might be like following a normal distribution or some other kind of a pattern that's fairly predictable. So you go out and you collect data, and you look at that experimental data, call that your observed results, and you think, well, it doesn't look perfectly normal, but I wonder how close it needs to be to actually be considered as normally distributed data. In other words, how close is close enough? Well, the chi-square test should be able to answer that question for you. Now, some other applications there, and I'm going to demonstrate one here in just a moment, but you have examples that you can work with where you have small configurations. The normal test would be kind of a big one, but you can do such things as chi-square tests of independence for little 2x2 tables. And there's lots of examples for that. But then as you move on to the work that we're doing, you're going to see examples for the chi-square test is used in conjunction with what's called the Wald test, to test the significance of model coefficients. You're also going to see it in logistic regression models where it's used to test the global fit of a model. You're going to see it with the deviance chi-square test, and then also with the likelihood ratio test. So you got some interesting places where this thing has kind of crept through time. Well, let me go back just a little bit here. Fisher had kind of a dilemma in that early part of the century there. He was looking at the work that Mendel had been doing, and other people were taking a look at this too. And there was some arguing going on back and forth about Mendel and how that work should be looked at. And then R.A. Fisher in 1936, he was looking at this, and he decided that he needed to go back and replicate some of the experiments that Mendel did. And then he would test it with the chi-square test. And so what he saw there was that he thought that Mendel's results were too good to be true. In other words, his experiments were coming much too close to what they actually should have been. There should have been some variability in there. And Fisher claimed that Mendel cooked the results. And the argument launched from there. People began to look at that, and they would line up on one side or the other and say, oh, no, Mendel was right on track with his experiments. And others would say, no, Fisher's right. And there's been a whole bunch of articles published on that. Fisher's dilemma. Okay, enough of that. There's two things needed to perform chi-square tests. You need, first off, a test statistic, something that you're going to use to measure the deviation of your sample or observed data from a hypothetical population value, which would be what you would consider to be the expected values. Secondly, you need a probability distribution, which helps you judge whether that measure, that difference there, could have occurred just by chance, or is it too big and it's outside the range of what you would expect. So here's what Carl Pearson came up with. And the test statistics that he derived or developed there was to sum the deviations between observed values, observed counts, and what would be expected counts. And he would square that number, divide by the expected count, and add them up over all the cells where he was making the comparison there. So that's his formula. And one of the things that happens when I use Markdown is those parentheses seem to get a little bit blurred. So bear with me. I haven't figured out a way yet to correct that, but you can see what it should be. Observed count minus expected count squared, add them up. Each of them is divided by their expected count too. In case you don't know what that statistic represents there, it is the sum of independent, identically distributed, normal, mean zero, standard deviation, random variables. So kind of a long explanation, and if you don't care about that, you don't need to know it. That probability distribution, though, that's derived from that is what's called the chi-square distribution. And I put down there the properties of the chi-square distribution too. It has one parameter called degrees of freedom. It is a continuous probability distribution. It is non-symmetric, and its limits are 0 and plus infinity. And I'll show you a plot of that here next, what that looks like for different degrees of freedom. But here's the Python code that generates that. And you can see what I've got listed there at the top of the screen, and then the Python code that comes along with that. And then down below, you can see a plot of that distribution. And you can see the picture there for different degrees of freedom. Now, the one that I'm going to use here in just a moment is the one for degrees of freedom equal to 1. And that's the kind of a blue plot in there. And it peaks up there where you can't see it. But then it drops down, and extreme values in that distribution with 1 degree of freedom are going to be numbers up there well above 4, something, in the 5 or 6 range. So if you have an experiment with the chi-square distribution and the degrees of freedom is equal to 1, and you get a result that's 7 or 8, you're going to know that's a pretty significant number there. All right. Here's some example tests that we typically would work with. Lots of examples out there, but probably the most common one is what's called a 2x2 contingency table. And again, what you're looking for is you're going to look at observed counts versus expected counts. And you have to have some way of coming up with what the expected count would be. And if you don't have any other information, then your expected cell counts are calculated by taking a row total times a column total divided by the overall total of all of the numbers in that table. And you'll see an example here in just a moment. But the hypothesis then will state that there's no difference between observed and expected counts. And the chi-square then is going to measure whether that's true or not. And we'll show how to calculate that. It's also sometimes called a test of independence. And what you're saying then is that we're going to test to see if this classification variable in a 2x2 table is independent of that classification variable there. Degrees of freedom for these tests is calculated by the number of rows minus 1 times the number of columns minus 1. Or in terms of a formula, it's R minus 1 times C minus 1. And so for a 2x2 table, it's 2 minus 1 times 2 minus 1, and that's easy to calculate. All right, here's the numerical values for this example. I got my little 2x2 table here, and people responded by gender, and they either indicated yes or no. And so I read in that table here with some Python code, and then I printed out the table so you could take a look at it. Now, The calculations that I'm going to show you here come from a book by Siegel called Nonparametric Statistics, and you can probably find that in a library somewhere if you want to look this up. But if I reference those values in a table as A, B, C, D, then the way you calculate that test statistic is in this formula right here. And N is the sum of all of the values in there, A plus B plus C plus D. And there's one other thing that's in here. It's this N over 2 is a continuity correction, because what you're doing is you're putting this in terms of a continuous distribution, and you're applying it in a case where the data is a little bit smaller and it doesn't really fit well with a continuous distribution. So this was developed over time and it works quite well. So here's your formula for this test statistic. Overall N multiplied times cross multiplication AD minus BC minus that continuity correction, quantity squared, and then it's A plus B times C plus D times A plus C times B plus D. So all of those that go into that calculation. And you can check that out if you want to run that through the example I'm going to show you here. So you enter your data. It's probably easiest in Python if you do this as an array. And I put an observed array up there with these numbers: 60, 55, my top row, 40, 45, my second row. And then I'm going to use this calculation here for chi-squared from stats, and I already have that put in up above there to load that in as one of my packages. And I'm asking it then to show there what is the chi-squared value, what is the p-value, what is the degrees of freedom, and then I want it to calculate the expected table also. And it will use for that the observed table, which I put here as this array. And then I did some formatting in here so that when the numbers print out, they'll look good. And it'll also print the expected table. So here's the results then for that table. My test statistic is 0.33, and you know that's not going to be significant for a chi-square test with 1 degree of freedom, because we know it has to be something up there in the range of probably 6 or 7. And my p-value, not really very small either. And so this thing is going to say, there's no difference here between gender and yes/no responses for that particular table. All right, down below I did a couple of things with the hypothesis test here. Calculated out the degrees of freedom and talked a little bit about the p-value there. But a couple of ways you can state this then is that in terms of the yes/no response is that it is really independent of gender. There's no relationship there that would show a dependency on gender. Another way to state it is to say, well, yes/no response is not contingent on gender. So some of the verbiage that has been built up over time on that topic. So now you know the language of it, and it's called a contingency table. It's also called a test of independence. Okay, a couple more things to tell you about here. You kind of need to be aware of some of these things. If you just go out and collect more and more data, you will get larger and larger chi-square values. So, and you'll get smaller p-values, which means you'll have more evidence against the null hypothesis. So chi-square tests are there. They will determine if an association exists, but they don't measure the strength of that association. And they do depend and reflect that sample size. So if you double it, you're going to double the chi-square statistic, even though that association doesn't change. And so another thing that you can look at is what's called the Kramer's V statistic. And a lot of software packages will calculate that for you. And I give you a little information there about the Kramer's V. Here's the interpretation of the p-value. You guys are probably already know all of this about p-values. But in case you didn't, I put it in here. You can read through this again. Another note of warning is about nominal versus ordinal data. Nominal data is categorical. That's like what we did here. It has no logical ordering. If, on the other hand, you do have what's called ordinal data, order is implied by the values there, then you need to use what's called the Mantell-Hansel chi-square test. We didn't have that in this case here, and so the regular old chi-square test was appropriate for this. So there's a lot of other directions you can go with this. One more thing here you need to know about. There's times when the chi-square test may not be appropriate. If more than 20% of the cells have an expected frequency of less than 5, then you're in trouble. Don't try to be using that chi-square test. But that doesn't necessarily stop you. In that instance, you can use another test here that's called Fisher's exact test. And it's based upon the hypergeometric distribution. And if you want to know more about that, again, you can see that book by Siegel on nonparametric statistics. So lots to think about and look at there. And the overall conclusion is that you should not be using gender to make a prediction about yes/no response from this particular data. Now, to build more complex models, we're going to use logistic regression. So just a quick introduction for you, and I'll also supply for you a copy of the code in an HTML file. So I'm going to stop sharing here and end this presentation.